Okay, so we're gonna look first at reviewing. We'll do ionic first, um, and then we are going to move on to molecular. Okay, so I'm gonna just copy this. I'm gonna put this on here just so I can write. For some reason, my tablet's a little bit funny. I have to write it in here. Okay, so the rule for figuring out formulas for ionic compounds is something that you might have heard of, something called the crossover rule. Okay, and that's where you look at the charge of each element or thing in the compound. And where you get that, I don't know if you're going to be asked to memorize that, but where you would get that is from a periodic table. Okay, so can you ladies see this periodic table? Just one of you say yes or no.
Yes.
Okay, good. Okay, so if you look at this periodic table, you'll notice that it has charges. For example, like sodium, you could see has a charge here of +1. Magnesium has a charge of +2. If I scroll over to this side, you'll notice that, like for example, aluminum has a charge of +3. Okay, this periodic table has a lot more stuff than you would see on your table in grade 9 or 10. To be honest, even grade 12. It's got some of these other really funny charges. Like normally chlorine would just be -1, but you see it's got a whole bunch of other charges, okay? So if you have a periodic table at home in your book, it would look almost identical to this, but it's just gonna have, like for example, for the halogens, which is the second last group over here, you're not going to see all of these charges. You'll just see -1. And for the group that includes oxygen and sulfur, you probably just going to see like -2. And then you can see -3 for nitrogen and phosphorus, okay? Now, the reason why that's important is because you need to know the charge to figure out the formula for ionic compounds. So sodium is +1 and fluorine is -1. So the crossover rule says that you just need one of each. So you would write sodium fluoride as just simply one of each, one, which would be NaF. Okay. Calcium, if you look at your periodic table, calcium is +2. Oxygen is -2. So the crossover rule predicts 2 of each, but with ionic compounds, what you can do is you can actually reduce them. So if they're the same number, you can just simply have one of each, right? So 2 and 2 would give you 1 and 1. The same thing with aluminum phosphide. Aluminum is +3, and phosphorus is -3. So then you would just need one of each because it's the same number. It's just the ALP. Zinc oxide. Zinc should be +2. Let me just double check. Yeah, zinc is +2. So that would be +2. Oxygen is -2. So it's just one of each. So it would be just, well, sorry. I'm sorry. We're naming in this case. This is going for formulas and this is going for naming. I apologize. So naming, the rule is, as you can probably tell from the first 3 examples, the only thing that changes is the second element. Now, this is what's called, these 3 examples are what's called binary compounds. They're made of 2 things. The first thing on the left is a metal, and the second thing is a non-metal, okay? And you can see from these 3 examples, the only thing that changes is the non-metal name, and you add an IDE ending to it. So zinc would not be zinc oxygen, it would be zinc oxide. Sodium, that's Na, and then that's selenium. So if you look at your periodic table, if we find Se, so Se is over here, it's selenium, so it would be a selenide, sorry. This would be lithium, and nitride. So you can see it's just the second, the non-metal is changing its name to an IDE ending. Now, in addition to ionic, there are what's called the binary compounds that include transitional metals. Okay, so these are the metals that have more than one possible charge. So for example, if I look at gold in the periodic table, gold being AU, you'll notice it has two possible charges. It's +3 and +1. So if it's got more than one charge, what you do is you use a Roman numeral, so you identify what the charge is. Otherwise, you don't know. It could be +1, it could be +3. In this case, it says that gold is +1. Now, chlorine, which is chloride, is this chlorine that's picked up one electron. If you look at your periodic table, chlorine is -1. And this says gold is +1. So you have one of each, right? So your formula would just simply be AuCl. If I look at the next example, it says cobalt is +3. So the 3 means that cobalt is +3 and chloride is -1. So that means we need 1 cobalt and we need 3 chlorine. Okay, again, you're just using the simple idea of the crossover rule, where that charge goes here, right? And this charge basically determines the number for the other element in this case. Lead 4 sulfide, that means lead is +4. And if you look at the periodic table, sulfur is -2. So that would mean that, and lead is, so lead's Pb, S is for sulfur. So the crossover rule says we need 2 lead, 4 sulfur, but with ionic compounds, you reduce them. So I can divide both numbers by 2, and that would give me PbS2. If we look at the last example, and on this screen there's more, then you can see it's CuCl2. So this is actually where we go into the opposite, where we actually go from the formula to naming them. But let me actually just go back to my Word document. Any questions at this point? Okay, so then let me go back to this. Let me just show you some more examples. We'll look at the opposite. So just take a screenshot of this. Okay. Sorry. Wrong button. Okay, here we go. Okay, so here are these 3 examples. These 2 examples, we just do the opposite, right? We go from the formula to naming them. So this says it's copper, Cu is copper, and it's chloride. Okay, now copper, if you look at your table, copper is a transitional metal. It's got 2 possible charges, right? So then what is it? Well, there's a hint. So if we go in reverse order, the crossover rule predicts the charge. So look, there is no number here, right? I don't see a number here, which means that this would have been -1, because we know the non-metal is going to be negative. There is a 2 over here, which means this would have been +2. So that tells us that copper is copper 2 chloride. Okay, we can apply the same logic to the next question. So there's a 2 over here. I'm gonna make this a little bit bigger. Okay, maybe not. It's not getting bigger. Okay. All right. So I don't know why it didn't increase in size. Okay, so here we go. So here's iron. It's 2, which means that this was -2. And there's a 3 over here, which means that this is +3. So that tells us that that is iron 3 oxide. Now, I saw from the chat that it seemed that the polyatomics were a big issue. Is that what I'm getting? Is that the case? So let me see. Yeah, I see. Yeah. Okay. Okay, so it says we guys went over molecular and ionic, but we didn't do polyatomic. Okay, cool. All right, so the polyatomics are actually, so I did put up a chart here that says common polyatomics. So let's just open that up. Okay, this is one of those things where I'll be honest with you, there's going to be quite a bit probably on this list. Let me just download it. Probably the best option. Okay, so sorry. So here is a bunch of different polyatomics, and you're not probably going to come across too many of them. There's only going to be a small set that you're going to use most often. Okay. It's with the polyatomics, it's kind of like teaching you how to learn your phone number. It's really one of those things where when you see it enough times, you're just gonna remember them. There are a few key ones that you're gonna see, but in terms of the way you figure out the formula or the way you name them, it's actually the same method. So, for example, if I look at my polyatomic list, so the first example here is iron 3 sulfate, right? So if I go here, look for sulfate. So where is sulfate? Okay, so sulfate is, the last one. Okay, you can see on the sheet that it's SO4 2 negative, right? Whereas sulfite is SO3 2 negative. Okay, so if I go back here, sulfate is SO4 2 negative. Okay. Now the next one is carbonate. So if I look at the sheet, carbonate is, where is that? Carbonate would be up here. So carbonate is CO3 2 minus. So for the next one, it's going to be CO3 2 minus. And the other one in this example is phosphate, which is PO4. So if I go back to here, I look for phosphate. Phosphate is PO4 3 minus. Okay, so PO4 3 minus. Okay, so now the way you figure out the formula is exactly the same method we used in the previous scenario with ionic compounds, because these are still ionic compounds. Difference is not binary, but you still have a metal with something that's negatively charged, right? And pretty much all the polyatomics are going to be negatively charged. There are some examples. If you look at the list, there are a few, I think maybe only one on this list. It is positive. You can see it up here, it's ammonium. Okay, so the way you figure out the formula is the same. It's just using the crossover rule. So for example, it says here iron is 3. So it's we know that means it's plus 3, and sulfate is minus 2. So the way you figure out the formula is you would need 2 iron. The crossover rule predicts we need 2 of these, and we're going to need 3 sulfate. Okay, so this is how you rate it. So here's your iron, and here's your sulfate. Okay, now, as soon as you need more than one, okay, as soon as you need more than one polyatomic, this is really important. Okay, what you do is you put brackets around it, and that's important. Okay, now so it says according to our crossover rule, we need 2 iron. So I'm going to put a little 2 here beside the iron. And it says we need 3 sulfate. So I'm going to put a little 3 outside the bracket. Now, this bracket is important because what this means is that I have 3 sulfate. That number 3 applies to everything in the bracket. Okay? So if you look at the next example, so the next example would be magnesium carbonate. So the magnesium is, from your periodic table, is plus 2. And the carbonate is -2. So because these two numbers are the same, we know they're going to cancel out. So if you only need one polyatomic, then you don't need brackets. You could just write MgCO3. Okay, you only need brackets when you have more than one polyatomic. So if you look at the next example over here, you'll notice that there are brackets around the phosphate because you have more than one phosphate. All right. Any questions about that? I'll just keep looking at the chat. We can do some other examples. For example, let's say we had ammonium. And let's say it's ammonium sulfate. Okay, so according to the periodic table, the just from here, ammonium is NH4 plus. Okay, so ammonium is NH4 plus, and we know sulfate is SO4 2 minus. Okay, so this means that we're going to need 2 ammonium, and the plus, we know if there's no number, it means 1. So therefore, we're just going to need 1 sulfate. So the way you would write this is you would write ammonium. Now we need 2 ammonium, so we're going to put brackets around ammonium. I'm going to put a little subscript 2. Okay. The sulfate does not require brackets because it only has 1. Okay. So let's look at 2 examples then of the opposite, where you have the formula and then you want to name them. Okay. So here is CO is cobalt, so cobalt, and then PO4 is phosphate. Okay. Now if you do the reverse crossover rule, we know that this 3 came from phosphate, and that 2 came from cobalt, right? That's the reverse crossover rule. So that tells us then that cobalt is, I believe cobalt is a transitional. Yeah, no, sorry, cobalt is not a transitional. So you do not need to use, I thought it was transitional. So you do not need to use a Roman numeral in this case. But if it was transitional, then you would put the Roman numeral 2. I could have swore I thought cobalt was transitional, but maybe I'm going crazy. Being at home is driving me a little bit crazy. So, okay, let's look at the next one then. So again, you don't need a Roman numeral for cobalt because according to this periodic table, it is not transitional. But if someone wants to look that up and double check that, feel free to just chime in, okay? Let's look at the last one for this set, which is SnSO4. So again, there's a 2 here. So we know that 2 came from here, plus 2. Now, here's this one's a bit tricky. I'll tell you why it's a little bit tricky. Because we know that sulfate is -2, right? So we know that sulfate is -2. Now, if we looked at it and said that, well, okay, let's just do the reverse crossover rule, and let's just go in the opposite direction. I know that's a +2. Then we would have a problem because the formula would predict SnSO4 because these two numbers are the same. But it clearly says that it's not SnSO4. It's SnSO4 bracket with a 2 on the outside, which means then that this cannot be +2 It has to be +4. Now, we can easily check that because if we have SN as being +4, for example, and sulfate as being -2, then that would predict we would need 2 SN. By the way, SN being, if you look over here, SN is 10, okay? SN. So we need 2 tin, and we would need 4 sulfate, but because it's ionic, we can reduce it, divide everything by 2. So that would mean, yeah, you would need 1 tin and 2 sulfate, which is what this formula is showing. So that's correct. So you can always check to see if that makes sense. Is tin +2, if I use the reverse crossover rule, it doesn't make sense in this case. So it's not +2, maybe it's a multiplier of +2, maybe it's +4. Now, if it's +4, then that tells us that the name for this would be tin 4 sulfate. Okay? All right. See, let me just check the chat. Yeah, this is, I think cobalt is transitional. I think so too. I remember it being transitional. Thanks, Nikita. So so for some, that's weird. For some reason, this periodic table does not show it as transitional. But yeah, I remember it being transitional. So let's go back then to that with cobalt, and then we'll just finish that one off, okay? So yeah, cobalt is transitional. Therefore, in this case, we would write the Roman numeral 2. Okay? Okay. Is that okay so far? Do you want me to do some more? Or should we just quickly review molecular and then we're going to move on to the next topic? Okay, so let's look at a quick review of molecular. Molecular, to be honest with you, is actually it's quite easy because you're told exactly what the formula is with the prefixes. Just there are a couple of rules to remember with molecular. The second thing is in the molecular compound has the IDE ending. Okay. The other thing is there's no 2 vowels in a row. So so what that means is that if you look at, for instance, something like this, like you would not say mono, because there are a bunch of prefixes, mono being one. You would not say mono oxide. You would just see there's 2 vowels in a row, so you just drop one of the vowels, it'd be monoxide. So the prefix tells you exactly how many of each you need. So in this case, dinitrogen monoxide would simply be N2O, because we just need 1 oxygen. And if there's no number in front, that obviously means 1. So the next one would be P with 3 chlorine, right? Tri. Sulfur hexafluoride would be S. There's no number. Oh, sorry, no prefix. And hexa means 6. Okay. Tetra. See how notice there's no A, tetra. So we drop the A. So it's not tetraoxide, it's just tetroxide. So it says we need 2 nitrogen and we need 4 oxygen. Now, let me pause here. Notice one thing that's different about this and molecular. We don't reduce molecular compounds, okay? If it was ionic, you would reduce it. You would divide everything by 2. But for molecular, you don't do that. All right, so don't reduce in molecular. It's very, very important, okay? Okay. Last one is diphosphorus. So P2 pentasulfide. Okay. How many of you know what this is? When you know, just spit it out. And I'll tell you a funny story about this. Let me check the chat. Yeah, thank you, Ella. It's water. Nikita and Ella, very good. Natalie, water. Wow, you guys got it really quick. Funny story. There was a radio station in the States that told their listeners not to drink the water because they put dihydrogen monoxide in it, and and people were freaking out. Can you believe that? Yeah. Anyway, so a couple of things about molecular compounds. There are some things have like official names. So, for example, there are a few of them. Um, so, like you know, if you, it's not wrong to say dihydrogen monoxide, but normally you would just say, in this case, you would just say water, right? For instance, this, if you had to name that, that would be carbon tetrahydride. But this actually has an official name, methane. Okay. So some of them have official names. You know, you're gonna come across them. You're gonna remember them over time. Some of the elements on the periodic table are diatomic. So, for example, like N actually exists as N2. O exists as O2. F exists as O2. So you wouldn't say dinitrogen, you wouldn't say dioxygen, you wouldn't say difluorine. You would just simply say nitrogen. You would just simply say oxygen. You would simply say fluorine, chlorine, iodine is another one. Hydrogen is another one. Okay. Bromine is another one. There's I think there's about 7 in the periodic table that exist as molecular compounds. They just simply are diatomic. Okay, but you wouldn't say dibromine. You would say bromine, and they're all gases except for iodine. Okay, now in the reverse manner, we can go from the formula to the name. So this would be disulfur, dichloride. Again, you change the last one. Okay. This will be tetra. We don't drop the A because phosphorus starts with not a vowel. Diphosphorus. Octa. Octa is 8. Sulfide. And then this one is carbon. And you don't need to see mono for the first one. Although I have seen it in there, sometimes you do see it, but you don't need to say it. So for the first one, it's carbon, and then tetra, but you drop the I. So you drop the A because it's tetraiodide. Okay. Let me see. I think there's a few more. So let's just record this. And then that's it. Oops, sorry, make this bigger. So then this would be dibromine. Sorry, dibromine. In this case, we have to say dibromine. Monoxide. We have to say dibromine because it's in a compound with oxygen. It's not by itself. The next one would be tetraphosphorus. I believe the prefix for 6 is hex. hex oxide. The next one is iodine. 5, so that 5 is pentafluoride. And the last one is tetrasulfur tetranitride. Okay. Any questions? Okay, so then what we're going to do is that's a review. I am recording this, so if you need to go back to it, because we are moving quite fast. But what I want to do now is I actually want to, because this is important, because the thing about chemistry is if one part like this falls apart and you don't really know how to name, or you don't know how to go from the name to the formula to the name, then it's going to mess up the next part. Okay. Because in the next part, what we're going to do is we're going to talk about how to go from like naming something to actually what's called balancing an equation. Okay. So when we balance an equation, what that means is we are going to go from something like this to a formula, or try to figure out how many of each we need. Okay, but we can't get there here. We can't get to this point yet because we need to do something first before we get to this point. What we need to do is we need to figure out a way to count atoms. Okay, so this is what we're going to do, and you'll see the tie-in. So I'm going to look at this sheet, and I'm going to look at how I'm going to show you how to count atoms in a compound. Okay. So, last time we talked about how to name them. So, for instance, that's important. So, for example, this would be potassium carbonate, and this would be barium phosphate. Now, that's important because what you may get is you may get the name, not the formula, and therefore you have to get the formula. And that's a really, really important skill. That's why the naming and figuring out the formula is the first thing you learn when it comes to chemistry, okay? Now, what we're going to do here is we're going to figure out a way to count the number of atoms in each compound, okay? So if you remember, the subscript tells you the number of atoms. So for example, I see there's a number 2 beside the K. But first off, let's do one thing. I see one potassium. I see potassium. I see carbon, and I see oxygen, right? Now, how many of each? Well, the little subscript for K is a 2, so that tells me there's 2 potassium atoms. There's nothing beside the C, so that means that's a 1. And there's a 3 beside the O. That tells me that there's 3. The total number of atoms in this is 6. Now, this is a really important skill, okay? The other way of looking at it is you could think of it as there's 1 potassium, which is true, and you can think of it as there is only 1 carbonate, okay? You'll see what I mean by that when we get to the section on balancing, okay? So we can think of it 2 ways. We can think of this as all of the atoms in the compound, so 2 potassium, 1 carbon, 3 oxygen, or we can say there's 2 potassium and there's 1 carbonate, okay? Now, if we look at the next example, we'll see the same thing. So we can look at it as there's barium, there's phosphorus, and there's oxygen. There is a 3 here, so we can say that's 3 barium. Now, you notice there's brackets around the phosphate, okay? So if you remember, that little 2 means that we have 2 of everything. So if I look at phosphorus in the bracket, you'll notice that there's a 1 because there's nothing there. So that means 1. But there's a number outside the bracket. So that's a multiplier. So that means we have 2's phosphate. sorry, 2-phosphorus. I apologize, 2-phosphorus. We do have 2-phosphate, but we're looking at P, phosphorus, okay? So there's a no number, which means a 1, so 1 times 2 is 2. Oxygen, in the bracket, there's a 4, and there's a 2 outside the bracket, so that means we have 8 oxygen. So if we look at it as just number of atoms, that would give us a total of 13. If we look at it as barium and then phosphate, and we don't think of the phosphate as separate atoms, just as one thing, as a polyatomic unit, then another way of looking at this is we have 3 barium and we have 2 phosphate. Okay, that's another way of looking at it. All right. Questions so far? I'll just keep checking the chat if anyone has any questions. Okay, so let's look at then the next one. Okay, so the next one is these two. Okay, so take a screenshot. Okay. Then when we get to the section on balancing, we're going to unite the two concepts of naming and doing what we're doing right now. All right. So CrO4. Whoa. Okay. What's that? Well, if I look at the, if I go back to this, the polyatomics. I told you that there's a lot of these you're not going to come across, right? But you know, eventually you're going to see enough of them where you're just going to remember. So CrO4, if I look at my my list, CrO4 is chromates right over here, okay? So that tells me that this is chromates. Now, I don't need that for what I'm doing here, but what if I, instead of giving you the formula, I said, tell me the formula for sodium chromate, right? So, because here we have the formula, but you know, you could be given the name instead. And if you think about what we did previously, you did, you know, you went from the formula to the name, but you also went from the name to the formula. So it's important that you know how to go in both directions. So this is sodium chromate. So if we go again to the count, right? We can think of it as there is sodium, there's chromium, and there's oxygen. And there's 2 sodium. There's nothing here, so that's 1 chromium. And there's 4 oxygen. That's one way to look at it. Another way to look at it is just simply sodium and chromate as a unit, okay? Which says that in this case, we would need 2 sodium and there's 1 chromate. That's another way to look at it, okay? The next example, I see just simply 2 elements, calcium and chlorine, okay? What's different about this example is we also have a number in front. Now, just like we talked about with the number outside the bracket, right? So let's say going back to something like this, where you have, let's say you have Na3. I'm just trying to think of one. No, that wouldn't be a good one. Let's say you have, okay, so like this, MgNO3, 2. Okay, this is something called magnesium nitrate. The number outside the bracket means you multiply everything in the bracket, right? So this 2 multiplies everything inside that bracket. A number in front multiplies everything, okay? So a number in front would multiply, let's say we had a number like 3 in front of here. So now if I said to you, how many nitrogen would there be in this sample? Well, it would be 1 times 2 times 3. How many oxygen would be in their sample? It would be 3 times 2 times 3, okay? So That number in front is just a multiplier of everything. So if I look at this CaCl2, there's no subscript for Ca, so we know that means 1. But there's a number in front, which is a multiplier. So that tells us there are 3 calcium atoms, okay? If I look at chlorine, it says chlorine is a subscript, so there's 2, and there's a multiplier in front, there's a 3. So that means that there are 6 chlorine atoms, so a total is 9. And I forgot to put the total over here, which is 7 in this case, okay? All right, are there more examples? There are a couple more. Okay, see if we can squeeze them all on the same sheet. Make it a little bit smaller. Okay, so let's do these last few examples. Okay, so if I look at here, this one does not have anything. By the way, the number in front, it's called a coefficient. Okay, it's called a coefficient. All right, so if I look at this, okay, so I see there's nitrogen, there's hydrogen, there's carbon, and there's oxygen, okay? So how many nitrogen are there? Well, it doesn't have any subscripts, and there's nothing in front, so that's simply 1, okay? Now, if I look at hydrogen, there's 4 over here, and there's another 3 over there. So in that case, I can add them up, and that gives me 7. If I look at carbon, there's just the 1 subscript, so that tells me that there's 2 carbon. And if I look at oxygen, there's just the 1 subscript, so that's 2. So the total number in this case would be 1 plus 7 plus 2 plus 2, so that would give me 12. Okay. If I look at the next example, it's Al, there is C, and there's O. Okay. Now, this one has a coefficient. So if I look at aluminum, it has a subscript. Okay. So the subscript is 2. Coefficient is 4. So 2 times 4 would give me 8. Okay. This 3 does not apply to aluminum because it only applies to the things in the bracket. So if I look at carbon, I'll notice that there is no subscript. So that means it's 1. There's a number outside the bracket. So that's a 3. So 1 times 3. And there's a number in front, which is a 4. So that means that there's 12 carbon. Okay. If I look at oxygen, there's a 3. So there's my subscript. There's a 3 outside the bracket, which means I have 3 of everything in the bracket. And there's a coefficient. So that would give me 9 times 4 being 36. So the total number of atoms in this case would be 56. But like I mentioned before, another way to think of something like this is that there are 8 aluminum, or we can look at it as being there's 4 times 3, 12 carbonate. There's another way to think of it too, okay? All right, 2 last examples. So here's, this is lead, and this is something called nitrate, okay? So if we do it by atom, we can see that there's no coefficient and no subscript for lead, so that means it's 1. For nitrogen, there's no subscript, that means 1 times the number outside the bracket, so there's 2. And for oxygen, there's 3, and there's a number outside, which is 2, so that gives us 6. So the total number of atoms in this case is 9. But again, this is an example where we have a metal with a compound, so we can also think of it as if there was just simply 1 lead, and there were 2 nitrates is another way to look at it, okay? Last example would be this one over here. So this one, we can look at it as there's N, there's H, there's Cr, and there's O. So in terms of the N, there's no subscript, so that means 1. There's a number outside the bracket, there's your multiplier, and there is also a coefficient, times 2, so that gives us 4. For hydrogen, there is a subscript, 4. There's a number outside the bracket, and there's a number in front, so that would give us 16. And for chromium, there's just a subscript times the coefficient, that gives us 4. And for oxygen, there is a subscript times the coefficient, so that would give us 14. So the total number in this case would be 38. But in this case, actually also in this case over here too, I forgot to mention that the NH4 is actually a polyatomic compound. That's ammonium. If you remember, ammonium is, I think, the only one on your list that's positively charged. And I think the C2H3O2 is another polyatomic. I believe that is acetate. Yeah, it's right over here. So going back actually to this example over here, this can also be thought of as 2 polyatomics, where the NH4 is 1 and the C2H3O2 is actually a polyatomic on your list, which is right here, which you probably, not be honest, you're probably not going to come across that often, but you can see it's right there, C2H3O2. That's something called acetate. So another way to look at this one is that we have basically just simply one of each. There's one ammonium and there's one acetate. The reason why I'm telling you there's different ways to look at it is because when we do the balancing, sometimes you do not need to split up the polyatomics. When we get to some examples, you'll see what I mean by that, okay? Okay, so finishing off with this last example where we just looked at, it was 38, that's an 8, 38 atoms. The other way to look at it is we have NH4, which we know is ammonium. And how many NH4 do we have? Well, there's 2 times 2, so there's 4 of them. Now, the other thing is also a polyatomic that you're probably not going to come across that often. You can see it's right here, it's Cr2O7. It's called dichromate. So dichromate is actually another polyatomic. And in that case, how many do we have? Well, there's no brackets around dichromate, which means there's only one dichromate here, times the coefficient, which is 2. Okay? Any questions about how to count? Now, the reason why we're doing this is because we have to be able to count to be able to balance. You have to be able to name, you have to be able to do formulas, but you also have to be able to count to do the balancing part, okay? So this is where we put it all together, okay? And what we're gonna do is we're gonna try to basically make sure that the number of atoms is the same on both sides of this equation. So let me explain that. Let me close this, make this bigger. Okay. So what you have here is a chemical reaction, okay? I think you did chemical changes in grade 9. So chemical changes when you have chemicals that get together and they react and they give you something new, right? So In this case here, for example, there's always going to be an arrow sign. I don't know what happened there. It's always going to be like an arrow sign, okay? And that arrow sign just tells you the direction that the reaction is going. So this says that we have hydrogen, all right, and oxygen reacting to give you water, okay? Or you could say dihydrogen monoxide if you want. Remember, hydrogen and oxygen are diatomic. There are a few examples of diatomic elements on your periodic table, okay? Now, the idea behind this is really, really important, is that the left side equals the right side. Because in any chemical reaction, you have to abide by something called the law of conservation of mass. What that means is that the number of mass is like the amount of stuff, right? The amount of stuff on the left side is equal to the amount of stuff on the right side. Now, that simply just translates into this. The number of atoms on the left side equals the number on the right side. That's why we had to do the counting activity, because if you don't know how to count the number of atoms in the compound, then it's going to be very hard to know if it's balanced, all right? So if I look at, for example, this one here, okay? If I look at on the left side and look on the right side, I'll notice it's not balanced. For instance, there's two types of atoms I see, right? I see hydrogen and I see oxygen. So let me just do like a little table here, just so you see this. So let's say I do a table and I do left side and I do right side, okay? And I look and I have hydrogen and I have oxygen on the left, right? And on the right, I see hydrogen and I see oxygen, same thing. Now, from the counting activity, I know that there are 2 hydrogen on that side and there are 2 oxygen on that side, okay? Okay, on the right side, I see 2 hydrogen, but I only see 1 oxygen. So you'll notice that it's not balanced. The left side is not equal to the right side. So what I got to do is I got to figure out a way to make sure that they're the same. So the only thing I can mess around with when it comes to balancing, the only thing, this is important, okay? The only thing I can change is the coefficient. Okay? That's the only thing I can change. I can't cheat and take this oxygen and make it a 1. Okay, now it's balanced. I can't do that. So the only thing I can change is I can change the coefficient. So what I can do is I can put numbers in front. This is the coefficient that will allow me to balance this out. And how you do it, there's not one right method to do it. It's about going back and forth until the left side equals the right side. Okay? Eventually, you get better at it and you start seeing it faster, but there's really no right way to do it. So first thing I notice, for instance, is that the oxygen is not balanced. On the right side, I see it's only 1. On the left side, I see it's 2. So I'm going to fix that problem. What I'm going to do is I'm going to put a number in front that will make the oxygen equal 2. So what could I put in front that would make it equal 2? Well, that's easy. 1 times 2, right? If I put a 2 here, then I know that 2 times 1 gives me 2. So now I know that there's 2 oxygen on the right side. But the problem is if I put a 2 here, that changes this to 4, right? Okay, so now what I have to do is now I got to fix the hydrogen, because now you can see that the oxygen's okay, but the hydrogen's not. Okay, so now I'm going to go back to the hydrogen and I'm going to say, well, okay, there's 2 hydrogen here. If I put a 2 in front of it, that gives me 4. So now the hydrogen is balanced and the oxygen is balanced. This is completely balanced. Left side equals right side. I can do the exact same thing with the next one. So let's look at the next one. So the next example, we have, this is a different color. Nitrogen and hydrogen give you something called ammonia. Okay, not ammonium, ammonia. I can see on the left, I have nitrogen, I have hydrogen. On the right, I have nitrogen, I have hydrogen. Okay, that's so far so good, that's easy. I can see on the left, I have 2 nitrogen and I have 2 hydrogen. On the right, I have 1 nitrogen and I have 3 hydrogen. Okay, so I can see that the left side does not equal the right side. The number of nitrogen is not the same. The number of hydrogen is not the same. Okay, so let's start with the nitrogen. So maybe I can think about multiplying nitrogen by like 2, because that will give me 1 times 2 is 2, and that won't give me the same number as the number of nitrogen on the left. But if I put a 2 in front here, that would mean now that I don't have 3 hydrogen. Now I have 6. So what I can do then and go back to the left side and say, well, okay, what could I put here that will give me 6? Well, if I take 2 and I multiply it by 3, that will give me 6. If I put a 3 here, now this is also balanced. The number of nitrogen is the same, the number of hydrogen is the same, the number on the saves on the left as it is on the right. Okay. Let's skip down to number 6, which is a bit more challenging. Let's go down to that one, okay? And if anyone has any questions, because I know this is getting to be, a little bit lengthy now, feel free to ask. Okay, so on the left, we have 3 types. We have carbon, we have hydrogen, we have oxygen. On the right, we have carbon, hydrogen, and oxygen. Okay? Now, we have carbon dioxide and water gives us something. This is something called a sugar. Okay, don't worry if you don't know that. It's okay. And there's your oxygen. So actually, what this is actually photosynthesis, if you're curious. Right? This is how plants make food. Okay, so on the left, what do we see? Okay, I see 1 carbon. I see 2 hydrogen. Now, how many oxygen do I see? Well, there's 2 over here, and there's 1 more over there. So that's going to be 3 total, right? On the right, we have 6 carbon. That's not even close. We have 12 hydrogen. And we have 6 oxygen and another 2. We have 8. Whew, not even close, okay? So, all right, why don't we start with the carbon, okay? So let's start with the carbon. Again, there's really no right way to start, but let's start with the carbon because we can see they're all unbalanced. So let's put a number in front here that will give us the same number of carbon. So I know if I take 1, multiply that by 6, that's going to give me 6. So I'm going to put a 6 here, okay? Now, if I put a 6 there, what that's going to do is it's going to also change the number of oxygen now, because now it's 2 times 6. So now we have 12 oxygen from over here, plus another 1. That's actually going to change the amount of oxygen to 13, right? Because 6 times 2 is 12, plus another 1 over here, that's 13. Okay. All right. So the oxygen is like, oh, it's just really 13 and 8. Okay. You know what? But if I look at hydrogen, right? Hydrogen is 2 here and it's 12 there. So that's an easy thing to work with, because if I put a 6 here, well, 6 times 2, right? Or 2 times 6 is 12. So now, if I look at the number of carbon and hydrogen Those are both the same. So far, so good. But we have to go back now to oxygen, okay? So let's look at what we've done so far. So for oxygen, we have 6. We have 6 times 2. So over here we have 12 oxygen, right? 6 times 2. Okay. Now we have here, we have 6 times, there's nothing there. So that means 6 times 1. So that's another 6 oxygen. So that gives us now 18 oxygen on the left. Okay. All right. Well, let's look at the right side then. Okay. We know we have 8. We need another 10. Okay. So we have a number here. It says that the oxygen on the right side, you can see it's found in 2 areas. It's found here, but it's also found here. This is 6. So if I look over here, I have 6. So this, we know that these two now have to add up to 18, right? They have to add up to 18. So this number plus this number has to give us 18. Well, this is 6, which means that this has to account for 12. Okay? There's 6 in the oxygen. We'll fix that. Okay? I can see that there's 6 over here. And I know it has to be 18. I know I have to make this number 18 to balance it. I know I'm getting 6 over here, so I need another 12, right? So it's got to be 6 plus 12 to give me 18, because I want 18. I don't want 8. I want 18. So how do I get 12 from here? Well, this is 2. So if I put a 6 in front of it, I know 6 times 2 is 12. So now let's double check, okay? So I have 6 times 2 oxygen here. That's 12. I have 6 times 1 oxygen. That's 6. So I have 18 oxygen on the left. On the right, I have 6 oxygen for my sugar. So there's my 6. And now I have 6 times 2, which is 12. Is another 12. That gives me 18. It's balanced. It's totally balanced. Questions? I know this is a lot. Okay, let's keep moving on then. Let's take a look at, I don't need this document anymore. Let's take a look at then, well, I don't need that one either. Sorry, too many things open here. Let's go back then to this. And let's look at an example. Okay, we're gonna do an example with a polyatomic in it, okay? So here's the example we're gonna look at. And then we'll wrap up in a little bit, okay? So I know this is a lot. And this is my first of 4 Zooms today, so it's gonna be a long day. All right, let's look at number 14. Okay, I'm gonna do left side. I'm gonna do the right side. Okay. Now, if you can make your life easy, make it easy. Don't make it hard for yourself. Here's what I mean. If I look on the left, I see that there's aluminum. Okay, I see there's aluminum. Now, I also see that there's hydrogen. Okay, I can see that there's hydrogen here, and there's hydrogen in here, right? Okay. I can also see that there's oxygen. Okay. And on the right side, I also see that. I see there's aluminum. There's aluminum. I see that there's hydrogen. And I see that there's oxygen. Okay. But what I also notice, and this is where what I mean by make your life easy. Okay. I also notice that there's sulfate on both sides. There's sulfate here and there's sulfate here. So instead of taking the sulfate and splitting it up, what we can do is we can keep it as one unit. That will make your life easier. As you saw in the previous example, we did that. When we're doing the counting worksheet, you can split them up, but sometimes it might be easier just to keep them as a unit. So what I mean by that is, instead of writing the sulfur and the oxygen separate, write it as a unit, like this. Okay? So now we're going to go and I'm going to balance it. So let's start with this. On the left, I see that there are, let me just get rid of all this so we can make it easier to see. Okay. So I have 3 sulfate. Okay. So there's 3 sulfate. Now, on the right, on the right there's 3. On the left there's only 1. I don't see any brackets around the sulfate, so I know that that means 1. So first thing I'm going to do is I'm going to balance sulfate. Okay, I'm going to put a 3 here because now I know that 3 times 1 is 3. So now the number of sulfate is balanced. Okay. Now let's do the count of all the rest. All right. So I have on the left I have 1 aluminum. Okay. I have according to this I have 1 times 3. I have 3 oxygen. Sorry. And I have 1 times 3. So there's 3 oxygen over here, and there's 3 hydrogen over here. But there's also another 6 hydrogen, right? Because look, 2 times 3, that would be another 6 hydrogen. So what I have is I have 3 oxygen and I have 6 hydrogen. Okay? On the right, I have my sulfates taken care of. And I see that there's a little subscript. So there's 2 aluminum. And on the right, I see there's just 2 hydrogen. And there's just 1 oxygen. Okay. So here's what I'm going to do. I'm going to go now. I know that the sulfate looks okay. So now I'm going to balance the aluminum. Okay. Because I can see it's 1 here and there's 2. So I'm going to multiply that by 2. And that will be balanced out. So what I'm going to do is I'm going to put a coefficient here, 2. Because now I know that 2 times 1 Al is 2 Al. So now the aluminum is balanced. Now, if I do that, what happens then is that because I put the coefficient 2 here, that means that now the number of oxygen is not 3 here anymore, right? Because it's 3, but times 2. So it's actually now 6 oxygen. Right? That's going to change that to 6. And we had initially 3 hydrogen, and now it's also going to be 3 times 2, so another 6. Now there's not actually 6 hydrogen here by itself, right? Plus the 6 hydrogen from over here. That's going to actually change it now to 12 hydrogen. Oop, why am I writing H? I need to write H. So let me just double check. That's 6 and 6 is 12. Okay, so now what I can do now is I can go back to the right side. And because so far I have the aluminum is balanced. So this is okay, and that's okay. I just have to balance these two. But I'll notice something. This is 2, and that's 1. This is 12, and that's 6. So the ratio is the same for both. 12 to 6 is the same as 2 to 1. So what I can do is if I put a 6 here, I know that 6 times 2 is 12. So that would be the same number of hydrogen on the left. But whatever number I put in front, multiply by everything, right? So 6 times 1 is 6. So that would mean now that everything is balanced. And this is what I mean about making your life easier. We did not need to separate the sulfate into S and O. So if you see that it's on both sides of the equation, then don't waste your time separating it. Well, so for example, in 16, which we won't do, I'll let you try it. I'll notice that there's sulfate here on the left and there's sulfate on the right. I also noticed that there's hydroxide on the left and hydroxide. So hydroxide is one of those polyatomics too on the chart. So in this case, I actually can keep the sulfate and the hydroxide without splitting them up, keeping them on both sides of the equation. Okay, so what we're going to do is this. We are going to then look at just one example of like going the opposite way, and then we're going to wrap up because we are like, what are we at? Like an hour and 15 minutes in, okay? And it's quite long. So what I'm going to do is I'm going to scroll down, and I'm going to look at maybe some examples. I said one. Yeah, let's just do one, okay? Because this is getting long. But the idea is the same. The idea is you have to balance it out. So I'm going to look at one of these where we're just going to go the opposite way. So instead of getting the formula, you're just going to get the name. Okay? So for example, and some of these, if you don't know, just look them up. Look up the name for now. I mean, like I said, eventually you'll just learn. Like sodium peroxide, like how often are you going to come across that, right? So sodium peroxide is actually Na2O2, okay? But some of these, you're not going to come across them that often. So let's look at something like, let's look at, okay, let's look at number, I'm just trying to think of it. Let's look at number, let's do a tough one. Let's do 35. Let me zoom in on 35 then actually. So we're gonna do 35. Okay, let me do a screenshot. I'm gonna zoom in to 35. Okay, so we're gonna zoom in on 35. Okay, now, so let me look at left side and let me look at the right side. Okay. First thing we have to do is we have to write this out as an equation. Now, this is a PDF, so it's actually a little bit harder to work with. So what I'm going to do is I'm going to write the equation up here, okay? So this is an example of where you have to know how to go from naming to formulas, right? So aluminum sulfate is Al, sulfate is SO4. I know aluminum is +3, and sulfate is -2. So that's going to give me a formula of Al2SO4 3. Okay. Calcium hydroxide, that's the next compound. That is, let's see if I can make this even bigger. We know calcium is Ca, and hydroxide is, if you look at the polyatomic chart, hydroxide is -1. So that means we are going to need 1 calcium, and we are going to need 2 hydroxide. Okay, so let's start with that. I'm going to write this down, okay? So I'm going to write down Al2SO4 3, okay? Plus CaOH2, and that's going to give me aluminum hydroxide. These different colors. Let's use red. So aluminum hydroxide is Al. Hydroxide is OH. That's +3. That's -1. So the formula predicts we need 1 aluminum and 3 hydroxide, plus calcium sulfate. Calcium is +2, and sulfate is -2. Those two numbers are the same, so we just need 1 of each. Okay, now here is a good example again of where we have sulfate on the left and on the right, hydroxide on the left and on the right. So make your life easy. You do not need to split these up. Keep them together. So what we can do is we can do a count. We can say, all right, well, on the left we have aluminum. we have calcium, we have sulfates, and we have hydroxide. Okay, on the right, we have aluminum, we have calcium, we have sulfate, and we have hydroxide. Okay, so when we do the count, we'll notice that on the left, there are 2 aluminum. Okay, on the right, there's only 1. And this is what I meant before by, like, if you didn't know how to write the formula, like if I gave you the word and you couldn't write the formula, then you wouldn't be able to balance it, right? So to be able to balance questions, you need to know how to go from name to formula, but then you also have to know how to count the number of things in the compound. So to balance, you need those 2 skills. You got to know how to write the formula. You also got to know how to count in the actual number of things in the compound. Calcium. On the left, I see 1. There's no subscript. Okay. On the right, I don't see a subscript, so there's 1. Okay. On the right, on the left, there are 3 sulfates. On the right, there's only 1. Okay, there's no subscript, there's no brackets around sulfate over here, so there's only 1. On the left, there are 2 hydroxide. On the right, there is 3, right? There's a 3 right there. Okay, so let's start with the aluminum. Okay, you don't have to start with aluminum, but I'm just going to start with aluminum. So I'm going to multiply the, let me fix this. So I'm going to put a number in front. Remember, you can only change coefficient, right? I'm going to put a number in front on the right side. I'm going to put a 2 because 1 times 2 gives me 2. So if I put a 2 here, that's going to give me the same number of aluminum on the right side as on the left side. Okay. Now, if I do that, that's going to change the number of hydroxide, right? It's going to change the number of hydroxide from 3, because it was initially 3, to 2 times 3, which is 6. Okay. All right. Now, aluminum is balanced, but you can see that the sulfate is not balanced. So what I can do then is I can put, I can try to balance the sulfate. So I can put a number, because there's this 3 sulfate on the left, right? So I can put a number on the right to balance it. So if I put a 1 times 3 on the right, so if I put a 3 here, that's going to balance the amount of sulfate, right? Because that's going to give me 3 sulfate on the right. There's 3 times 1 on the right, and there's 3 on the left, and we're good. So sulfate's balanced. Now, if I do that, that changes the amount of calcium. If I put a 3 here on the right, that's going to give me not 1 calcium now, it's going to give me 3 calcium. Okay. So I can see that aluminum is balanced and sulfate is balanced. I just need to balance the last 2 things, right? I need to balance the calcium and the hydroxide. Well, all I have to do now is put a number in front of calcium hydroxide to balance it out. So there's 3 calcium on the right. So if I multiply this by 3, that will balance out. And if I did this right, that means the hydroxide should also be balanced, because that number 3 multiplies everything. So it multiplies the number of calcium, but also multiplies the number of hydroxide, right? So that's going to be now 3 times 3. That's going to give me 6. So everything's balanced. Left side equals right side. All right, how about that? Why don't we stop there? I'm tired. I'm sure you ladies are tired too. I'm actually going to stop recording this, and then I'll take questions, okay?